All right, we should be back by now. All right. Okay. Let's all remind ourselves to try to turn our homework in on time, folks. As of right now, I still only have like 5 or 6 of the section 3-2 homework.
Hey, I don't know where this side of the room is.
I'm just saying. No, I can't remember if you did it. Last night? I saw you. Hey, no need to apologize because there's many other students in here. Shame. I know he gave me a nice like, I am so sorry for turning this in so late. And I'm like, you're like submission number 4 out of 12. Yeah. Trust me, you're in the top third still.
I'm called out right now.
I did get what? It's always funny. I put it to 0 and then I get. I'm like, ooh, gotta turn that in. So please don't take advantage. Please turn your homeworks in relatively close to the due dates. Now, that being said, our quiz is on Wednesday. Okay, our quiz is on Wednesday. Our quiz is just over derivatives. Okay, now we had a derivatives quiz earlier on this year, but that was finding the derivatives using the formula, or sorry, the definition of a derivative, that f of x plus h minus f of x all over h. This is going to be just using the derivative rules. Okay, just using the derivative rules. So that includes derivatives of polynomials, derivatives of e to the x, derivatives of trigonometric functions, derivatives using the derivative of rational functions, because we'll have to use the quotient rule, using the product rule, all that fun stuff. Okay? Yes, derivatives of trig are going to be on the quiz as well. But honestly, I literally have like 2 examples to go over, and the rest of the period I'll answer homework questions. I'll do whatever we need to do. Sound good? Tomorrow, actually, let me look at something real quick. Section 3.3. Here's the homework. I wonder, do I have a derivatives review? No, I don't. So, I don't think there's, does this jump to right to section 3.4? Yeah, so I don't have a derivatives review. So all I'm going to be doing tomorrow is just answering questions over the sections 3.2 and 3.3 homeworks, probably the 3.1 if you'd like to as well. We can go all the way back to there. So plan on coming with questions ready tomorrow for any of the derivatives homeworks, 3.1, 3.2, or 3.3. If there's no questions, I'll just pick and choose ones from the homeworks and see. That means let's review these ones.
Maybe.
Right. I'll try to take a look and see which ones. Honestly, though, if I'm looking at anything, I'm looking at the ones. Let me go back here. Why did that pop up?
No, it's just on. See my cable good? This morning you might want to.
My port is kind of wiggly there. I got a wiggly port. Why are you talking about showers over there, Muppet? You wouldn't even hear that. You didn't even do your homework. You didn't watch the videos. Now you're not even paying attention.
She has a jacket on. And it's like 70 in here. She has a jacket and a hoodie on.
What is happening? Why is this doing that? Okay. What is going on?
I don't know what you're talking about. My temperature's in my life. I want to sweat that backflip, but I'm still slightly cold.
Okay, because I cannot zoom in, I don't know why I cannot zoom in. Ooh, bet I can do it on here. Yeah, there we go. I'm talking about like these sets of problems. I know this goes back to section 3.1, but there's in each one of the homework assignments really early on, there's just differentiate this, find the derivative, bam, bam, bam. Just one after another. These are where I'm pulling the questions from. And honestly, I go back and I pull. If I chose to do the evens, I pull some from the odds. Heck, I've been known to just pull homework questions straight off and put them on the quizzes. So check these. Those are where I pull the questions from. So if I go to section 3.2, I'm talking about 3 to 26. Okay, all those are fair game. If I'm looking at section 3.3, 1 to 16. Okay, those are going to be the ones where I pull from for that. Okay, more of the algebraic type. And I got to be honest, that's really the main difference. Like, if somebody always asks, people always ask me, what's the difference between AP Calc and TCP Calc? This is the difference. AP Calc is very theoretical and very analytical and very like, okay, let's take this situation and apply calculus to it. This is the more algebraic, like more like, okay, just find the derivatives, boom, 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 go, go, go. Okay, less word problem-ish, more just straight up algebraic work.
Do math, not think.
Right, plug and chug, I would say. All right. So now we talked about derivatives, and the main derivative we looked at first off was this one, right? The derivative of sine is cosine. And also on Wednesday, I am not going to be giving you any sort of formula sheets. They've got to be up here, okay? All the derivative rules must be in your head. So maybe it might be a good idea to take some time to memorize those rules. Like the derivative of sine is cosine. That's an easy one to remember. And then we got to this. The derivative of cosine is negative sine. The derivative of tangent is secant squared. Those are main ones here. If I take the derivatives of the reciprocals, the derivative of cosecant is negative cosecant cotangent. The derivative of secant is secant x tangent x. I always remember that the reciprocal ones always have themselves in it. And I always think that's weird, but that's just something to remember. Like the derivative of cosecant has cosecant in it. The derivative of secant has secant in it. They have themselves with a version of tangent. The way, and I know I'm just, my brain works in weird ways, but these are the things that I remember. The cosecant, the derivative has the cotangent in it. That's just the way I remember it. And the secant has secant and then the regular tangent. The cosecant has a cotangent in it. And then secant has just the tangent in it. It's self and tangent. And then how do we remember the tangent to the cotangent? If you remember that tangent is secant squared, then cotangent is cosecant squared with the negative in front of it. Right? You just got to remember which ones are negative. Okay. So again, and this is just the way my brain works. These two are cosecant and cotangent are negative. Cosine is negative. So all of the cos are negative. That's the way my brain works. All of the cos are negative. Cosecant is negative, cosine is negative, cotangent is negative. All of the regulars are not. Sine, secant, and tangent are not. Again, just, I don't know. You memorize them how you want to, but that's just what the way my brain remembers it. Then we did this problem where you just kind of have to figure out where the trigonometric identities are within them. Honestly, this is the calculus part. This is just reducing it down, right? The calculus part is just applying the quotient rule to it, and then we're just reducing down. We looked at this cool problem with the spring. Yeah. I can't remember if I give that. I'll have to look back and see. Let's see. Oh, that's right. I remember somebody from last year talking about it. You definitely gave that. Yeah, that's right. And then we did this cool problem with the spring where we pulled it 4 centimeters past, and then it went back and forth, and we saw the graphs. We did this problem. Come on. We did this problem last week, right? We did this on Friday, the 27th derivative. Oh, that's right, because Hudson was in here when we were talking. All right. So here's the 2 new problems, example 5 and example 6 down here. Okay. Now, to do this problem, we really need to learn one. You could call it an identity. You could call it a rule. I don't care, whatever you call it. The book, now, if you'd like to see, just like I said on Friday, if you'd like to see any of the proofs for these things, the proofs are all in the book. Like, I wonder if I could get back to this one here. The proof for, oh, it doesn't even have it in here. Oh, whatever. But all the proofs for the, like the cosines, cotangent, all that stuff, it's all the rules are always in the book. But one of the things that we have to learn, we have to know to solve this problem here, the sine of 7x over 4x, is that the limit, this is something you'll probably want to remember. Why is it doing that? Okay, I can write down here apparently. The limit as theta goes to 0 of sine theta over theta is 1. Okay, that's an identity that you need to learn, that you need to commit to memory. It only works for sine. It does not work for cosine or tangent or any other trig ratio. The limit as theta goes to 0 of sine theta over theta. Now, if I were to try to calculate this, the limit as sine theta over theta goes to 0, or sorry, theta goes to 0 for that. I cannot do direct substitution, so I'd have to figure out another way. Again, the proof is in the book. The proof, if you'd like to see it, is in there. But we can just memorize limit as theta goes to 0 of sine theta over theta is 1. Oh, that's why. It was earlier to prove the derivative of sine would be cosine. But right now we can just memorize it. Now it's going to be useful here. How do you know you're going to use one of these things? You use this identity, use this rule. Because I'm not actually finding the derivative in this next problem, am I? I'm just finding the limit as x goes to 0. Finding limit as x goes to 0. Understand that this theta could be replaced with any variable. The limit as a goes to 0 of sine a over a. The limit as x goes to 0 of sine x over x. So, if you know that rule, and then you look at this problem here, it's like, oh man, I see it in there. I see sine x over x in there, but there's different coefficients that are working on it, right? I want to take the limit as x goes to 0 of sine 7x over 4x. Now, excuse me, to solve this problem, right now there's a 4x in the denominator. I would love to have it because whatever's in here, notice that for the identity, whatever's in, stop that. Why is it doing that? Whatever's in here has to go down here. So like I need to have the sine of 7x over 7x. This can't be the sine of 7x over 4x. That doesn't reduce down. What it needs to be is the sine of 7x over 7x. So maybe what I can do here, not maybe, I'm telling you, the limit as x goes to 0 of sine of 7x over 4x. What I can do here is multiply by 7 over 7 to get a 7 into the denominator, because I need a 7 in the denominator to make this work out nicely. And I can do that because that's just 1. And I can bring it all the way into the limit because the limit of a constant is the constant. I can just multiply it in or take it out whenever I want, especially if it's 1. So that means this is 7 times sine 7x over 7 times 4x. The limit of that, right? Just going to work with it algebraically to put the limit back in a second. Well, look what I have on the bottom. 7 times 4x. I could make that 28x, but I'm not going to. If that's just multiplication, can't I just change around the order? And it's not going to change anything. So that's going to get us to 7 times sine 7x over 4 times 7x. I'm just going to group the 7x together instead of grouping the 4x. Now, when I go to evaluate the limit, that's the limit as x goes to 0 of 7/4 times sine 7x over 7x. Now do we see it in there? I'm just removing the 7/4 out in front of it so that I can clearly see the sine 7x over 7x. Now I've got this limit applying to both of those things. But remember, 7/4 is just a constant. And we learned based on our properties of limits that if you've got a constant within a limit that does not depend on that x value, like if I plug x 0 in for x of 7/4, it's just 7/4, right? The limit of a constant is the constant. So what I can do here is bring that all the way out in front, then apply the limit to it. The limit as x goes to 0 of sine 7x over 7x. And what is the limit as x goes to 0 of 7x over 7x? Sine 7x over 7x, that's 1. That's 1. Because of our rule here, limit as theta goes to 0 of sine theta over theta. Okay, that's just going right in there, getting 1. So this is 7/4 times 1, which is 7/4. Come on. What is happening? I can't even erase that. Good thing I don't have a lot of notes to do today, because that would be annoying. Questions about that? Let's use that one more time. Calculate the limit as x goes to 0 of x cotangent of x. Now, this is not so plain to see that I should be using that identity, that rule, that limit as theta goes to 0. The only way I see it here is I'm trying to calculate a limit and not a derivative. That's a signal that's saying, okay, maybe I have to use that rule that we just learned. Okay, now, I need to have it as a fraction, though, right? Because it's sine theta over theta. And it's sine, not cotangent, right? So maybe there's something else I need to use here. Well, what is cotangent? Cosine over sine, right? Because sine tangent is sine over cosine. So cotangent is cosine over sine, right? Cotangent theta is cosine theta over tangent theta. Okay, well maybe that'll help us then. That's now the limit as x goes to 0 of x times cosine x. Oh, not tangent, excuse me. I wrote that wrong. Oh my gosh. Let's do that. There we go. Sine. Okay. Cosine x over sine x. There we go. That's much better. Now, if I were to rewrite this, and again, I'm going to leave the limit behind for a second. This is really like x times cosine x over sine x, right? So my sine x is in the denominator. Watch what I'm going to do here. I am going to multiply both numerator and denominator by 1 over x. And I can do that because, again, that's essentially just 1, right? Multiplying the numerator and denominator by the same thing is totally fine algebraically. Now, when I do that, what happens to my numerator? I've got x times 1 over x. It cancels itself out. So I'm going to get cosine x over, now this is the fancy part, sine x over x. And now I see the sine x over x that I'm going to use. So let's apply the limit back to it. The limit as x goes to 0 of cosine x over sine x over x. And we learned that the limit of a quotient is the quotient of the limits. So that means this is the limit as x goes to 0 of cosine x divided by the limit as x goes to 0 of sine x over x. What is the limit as x goes to 0 of sine x over cosine x? Or sorry, sine x over x. Ooh, it's not 0, it's 1. So this is the limit as x goes to 0 of cosine x. And if it's over 1, that can just go away, right? Now we just have to evaluate that. The limit as x goes to 0 of cosine x. What is the limit as x goes to 0 of cosine x? Well, can I do direct substitution? Let's try to evaluate it. What is cosine of 0? What's the x value when the angle is 0? Ooh, it's Monday. Can't do unit circle on a Monday, right? Here's my unit circle. Here's degree of 0. What's my x value? 1. So that means this turns out to just be 1. Questions about that? And all of that came from the limit as x goes to 0 of sine x over x is 1. Or the limit as theta goes to 0 of sine theta over theta is 1. All of that comes from that identity right there. Okay? And you know you use that when I give you a limit. Like if I'm going back to these problems here for section 3.3, you might want to be using the 17, 18, 19, use that rule. No, I don't think you use that. Where's the limit problems? Maybe down here. Yeah, 39 to 50. You know you use that when you see the limit as x goes to 0. Okay? So you know you're going to be using it at some point down there. All right. That's it for today. I'll let you work on this assignment. That's not this assignment.